Remember from lesson 1.4, we had this figure, and we talked about the fact that if there is a current running through a wire, and especially if there is a changing current running through a wire, then there will be an electric field radiating away from the wire, and there will be a magnetic field around the wire, which also radiates away from the wire. And collectively, these fields are called the electromagnetic field radiating away from the wire. Now, the electromagnetic field, as we said before, is neither inherently good nor inherently bad. If it radiates into an adjacent trace and creates crosstalk, well, then that's bad. But if the adjacent trace is part of a differential pair, well, then differential signal coupling is good and the radiation is not bad. If the signal is radiating out into an antenna and the antenna happens to be at the FCC compliance testing range, well, that's bad. But if the antenna is in a radio or a TV set and we are exercising in communication, well, that's good. That's what electromagnetic radiation is all about. We also said in lesson 2 that current flows in a loop. If we simply have a driver and a receiver and a trace connecting them, current can't flow and a signal can't flow. But if we have a return path for the current, then signals can flow. And the corollary to that rule is that every signal has a return, and you need to know where that is because it's the return signals that account for most of our signal integrity problems. We also defined the concept of a loop area, and the loop area is the physical area within the current loop. If we have a driver and a receiver and a trace, and if the return signal is on the plane directly underneath the trace, well, then the loop area is relatively easy to define. It's simply the length of the trace times the height above the plane. But every signal has a return, therefore every signal has a loop area. Now, the reason that's important is that radiated electromagnetic energy, whether it's in the form of EMI or crosstalk or transmission lines or anything else, is directly related to loop area. Radiated electromagnetic energy, EMI, is directly related to loop area. This leads to a fundamental rule for minimizing radiation, and that is minimize the loop area. This is perhaps the most fundamental rule for signal integrity purposes in printed circuit board design, and we do that by routing every trace as close as practical directly over a continuous related underlying plane. That is our number one design rule in printed circuit board design for signal integrity reasons. Route every trace as close as practical, as close as your fabricator will let you, almost, directly over a continuous related underlying plane. And these adjectives are all important. Continuous means there's no breaks, there's no slots. Related means that we're not routing a digital trace over an analog plane. We're not routing a trace related to a 3-volt power supply over a 1.5 volt plane. And underlying, of course, means underlying. It's underneath the trace. In lesson 1.4, we provided these figures of the electromagnetic field under a variety of different conditions. And this was the one where we changed the height above the plane. If we have an 8 mil trace 50 mils above the plane, which is pretty high, then we had an electromagnetic field that radiated out in all kinds of directions. But if we brought it down close to the plane, within 5 mils, well, then most of the electromagnetic field gets trapped between the trace and the plane, and very little gets out. Route every trace as close as practical to a continuous related underlying plane. We also talked about the difference between microstrip and strip line. Here we have some traces, they're 10 mils above the plane, with a 50 mil separation, there's some radiation out into space, and there's some radiation and coupling between the traces. Put them in a strip line environment, and all of the electromagnetic field is captured between the planes. None of it gets out into the outside world, and very little here, none in this particular picture, gets coupled between the two traces. Now, EMI and crosstalk can look different. EMI looks a lot like the radiated signal, but a crosstalk signal is a lot more complicated. And here are some of the problems in understanding crosstalk. First of all, crosstalk is a point concept. It occurs at a point and then radiates away from that point. It has two different fundamental causes, and these causes generate two different signals. And these two signals flow in opposite directions, in two different directions. And the signals can interact with each other, and the two signals have significantly different shapes, and they behave differently as a function of the coupled length. And neither shape resembles the aggressor signal that caused the crosstalk in the first place. Aside from that, crosstalk is a piece of cake. So we're going to go through these points and talk a little bit about what really is crosstalk and why can it be a problem. First of all, crosstalk is a point concept, and it travels in two directions away from the point. Here is a signal, and it is propagating down a trace. We call this the driven line or the aggressor line. Here is an adjacent trace. We call it the victim line, and we're going to look at this point right here. At this point on the aggressor trace, this signal is just propagating by. At this point, this signal changes from a logical 0 to a logical 1, and that then causes capacitive coupling on this trace, and it causes inductive coupling at this trace. And so we have a capacitively coupled crosstalk that radiates away from this point in both directions, in the forward direction, which is the same direction the signal is flowing, and the backward direction, the opposite direction from that of the signal. And we have inductively induced crosstalk, which flows in the opposite direction from the signal that is causing it in the first place. And then the crosstalk signal is the combination of these two signals. So the forward crosstalk components tend to cancel. And we have one signal going in this direction. That's the inductively coupled signal. We have one signal going in this direction. That's the capacitively coupled signal. If those two signal components happen to be equal and they are opposite, then they would cancel. And in some cases, these components are exactly equal and they do cancel. And the most common way that happens is in a strip line environment where the environment is homogeneous or the environment is uniform. So it is usually the backward crosstalk component that is a problem on our circuit boards. And here we have an animation of a forward crosstalk signal. We have a signal that is propagating down this trace. It's coupling into the other line. And when this starts down again, right now, we have the signal that is propagating down the trace. It's coupling in at a point on the trace. As the signal continues to propagate, it continues to couple into the trace. But the signal that had coupled into that trace is also moving along at the same time and at the same speed. So they are moving together down these two traces, and the coupled signal reinforces the coupled signal from the increment before. And as we continue down the trace, we see that this continues to happen. We continue coupling in at this point. The coupled signal at this point continues to add to the coupled signals at the previous point. And this forward crosstalk signal continues to get larger and larger. until we get down here to the end of the coupled region. Now, the coupling stops, but this trace is longer than this trace, and so this coupled signal continues to propagate until it gets down to the end of its trace. And here again, we have the aggressor signal on this line, the forward crosstalk signal on that line getting larger and larger. The amplitude increases with the coupled length, but the width does not increase. The width is constant everywhere along this trace. It's just that the forward crosstalk signal keeps getting bigger and bigger. Here is an animation of the backward crosstalk signal. We have an aggressor signal that looks just like it did in the previous case. We are coupling in at this point. But when we couple in at this point, this signal starts moving backwards. That's backward crosstalk. So this signal starts going backwards. The aggressor signal keeps going forward. So we keep coupling in at a forward and forward point, but the signal then propagates backward from that point. So the signal that coupled here has been traveling backwards, going back in this direction. Now, we can kind of eyeball this and see that so far, the coupled length has been this long. So far, the backward crosstalk signal is twice that wide. The backward crosstalk signal width increases with coupled length, but its amplitude is not increasing. So we're going to let this free run a little bit more. We're at the end of the coupled region here, but this signal is going to continue going backwards. And then we're going to start over again. Now note that the coupling point moves forward, but then the signal that is coupled moves backwards. And so the width increases with the coupled length, and in fact, the width is twice as long as the coupled length, but the amplitude is not increasing at all. Now, what happens when the backward crosstalk signal gets to the near end? Well, I've got two illustrations here, and this is a continuation of the animation on the previous slide. In this situation, I have a driver at this end, but I have a termination at this end. In this simulation, I have a driver back here, but there is no termination. So this backward crosstalk signal is going to come back in this direction and is going to be absorbed in this terminating resistor. This backward crosstalk signal is going to come back here and reflect, and then come back up to the far end of the victim trace. Now we'll let this continue on and watch and see what happens. The backward crosstalk signal is being absorbed in this terminating resistor in this part of the simulation, but it's being reflected here and reflected up at the far end, and it is just now finally showing up at the far end. It took a fair amount of time for the backward crosstalk signal to propagate all the way back here and then all the way back to the front of the victim trace. And we're going to let this run one more time, at least for part of it. This is where we were at the end of the last animation. This backward crosstalk signal comes back and gets absorbed, does not reflect. This backward crosstalk signal reflects and moves forward and comes down to the far end of the victim trace. So what happens at the far end with backward crosstalk depends on what the situation is back here at the near end. The backward crosstalk may show up at the far end of the victim trace if it reflects off this end, the near end, but the backward crosstalk signal may not show up at the far end of the victim trace if the near end of the victim trace is properly terminated. Now, let's look a little more closely at the backward crosstalk signal. We're going to have a signal that is going to start to increase here. There's going to be a rise time here. And that immediately starts to couple as soon as the signal starts to change. It immediately starts to couple into the other trace. But we haven't reached the maximum value of the driven signal yet. So as we keep this going, this keeps rising up to a point. Then this no longer increases. This backward crosstalk signal no longer increases in amplitude. And then, after we get to the end of the coupled region, we have something that actually looks a little bit like a trapezoid that now starts propagating backwards. What we're going to find out is, let me get this a little bit further along. What we're going to find out is that the width of the backward crosstalk signal is twice the coupled length plus 1 rise time. There's a rise time here at the front end. There's a rise time here at the back end. This is kind of the opposite side of this rise time. And so this length here from this point to that point is twice the coupled region plus 1 more rise time. Now these signals behave differently, and we've just covered that. The forward crosstalk signal has an amplitude that increases with coupled length, but the width doesn't increase at all. The backward crosstalk signal has a width that increases with coupled length, but the amplitude increases only up to a point, and then it doesn't increase after that. And that point we call the critical length. The amplitude of the backward crosstalk signal increases up to a point. That's the critical length. Beyond the critical length, it doesn't increase any farther. And it is the same critical length that we talked about when we talked about reflections and transmission lines and controlled impedance traces. It's the same critical length. And neither of these pulses looks like the aggressor signal that caused it in the first place. Now, on the next few slides, I'm going to show you some crosstalk simulations. They were done with the Hyperlinks simulator. What we have is we have a driver. The driver is driving through a transmission line. That transmission line is terminated at the far end. We have a coupled trace nearby. This trace is coupling into this trace. This trace is terminated at the far end. This is the victim trace. It's terminated at the far end in a correct transistor. It is not terminated at the near end. Now what I have here is I have a 10 megohm resistor. That's here so I can hang an oscilloscope probe here so I can look and see what is going on in the simulation. But what that is simulating is an open circuit at this end. I'm going to provide a simple model here, and this is going to drive this trace with a ramp, and the ramp has a 2 nanosecond rise time. It's going to be a sharp turn on and then a sharp turn off, and it's going to look just like a very sharp ramp with a 2 nanosecond rise time. That's not exactly what a signal looks like, but what it will do is give us a very precise picture of what the crosstalk signals look like. And here's what the result is. Here's the ramp. And this is 1 nanosecond per division, so we have a 2 nanosecond rise time. And we have 3 different simulations here. And we have the results of 3 different simulations. And those 3 simulations involve 3 coupled lengths. 3 inches, 6 inches, and 12 inches. 3 inches is a half a nanosecond. 6 inches is 1 nanosecond. And 12 inches is 2 nanoseconds. And again, the ramp rise time is 2 nanoseconds. Now remember, I said that the backward crosstalk width is 2 times the coupled region plus 1 rise time. So in B, the backward crosstalk width is going to be 2 times the coupled region, or 1 nanosecond, plus a rise time, which is 2 more. So the backward crosstalk width for this simulation is going to be 3 nanoseconds. And this is that. We start here, and there's 1, 2, 3 nanoseconds. And that's the backward crosstalk signal rises, comes across, and falls again. C, the backward crosstalk width is 2 times the coupled region plus 1 rise time. So 2 times 1 is 2, plus 2 is 4. In C, we're going to have a 4 nanosecond pulse width. Well, it starts there. So there's 1, 2, 3, 4. That pulse is 4 nanoseconds long. This looks like a trapezoid. It increases in amplitude until it gets right here. Then at that moment, it looks like a triangle. And then it stretches out again and looks like a trapezoid again. But the amplitude stops growing at that point. In simulation D, we have a 2 nanosecond coupled region. So 2 times 2 is 4, plus 2 is 6. So this pulse width should be 6. And there's 1, 2, 3, 4, 5, 6. So all of this fits together just like it should. Now, let's take a typical case. I got a driver. I'm driving through a transmission line. I'm terminated here. I'm coupling into an adjacent trace. This is in a microstrip environment. I've got a 10 megohm resistor here so that I can hang an oscilloscope probe on it and look at the signal at that point. This shows the menu setup for setting up that transmission line. Here are my 2 traces. Here's the impedance of the 2 traces. I even get the differential impedance if I care and want it. There's the trace-to-trace separation. And here's the result of that simulation. The coupled region was 10 nanoseconds long. Here is the driven signal. Here is the backward crosstalk signal at the near end of the victim trace. If the coupled region is 10 nanoseconds long, then this signal should be 20 nanoseconds long. We have 5 nanoseconds per division here. So here is 5, 10, 15, 20 nanoseconds out here. So this pulse is 20 nanoseconds plus a rise time. The forward crosstalk signal is this signal. It shows up at the far end of the victim trace 10 nanoseconds later. That's the 10 nanosecond propagation time through the victim trace. And the backward crosstalk signal shows up at the far end of the victim trace at the same time. So it is showing up here. It's going to be 20 nanoseconds wide. So we go 5, 10, 15, 20 nanoseconds plus a rise time. So there's the backward crosstalk signal at the far end of the victim trace. So at the far end of the victim trace, we have the forward crosstalk signal, then we have the backward crosstalk signal showing up here, and everything starts happening 10 nanoseconds after the driver starts driving. That's the 10 nanoseconds of the coupled length. Now, for extra credit, why is the backward crosstalk signal at the near end bigger than the backward crosstalk signal at the far end? Here's the backward crosstalk signal here at the near end. Here's the backward crosstalk signal at the far end. You should already know the answer to that. The answer is this backward crosstalk signal has come back here and is being reflected. And the reflection is positive in sign and 100% in magnitude. So what we are seeing at this end is the backward crosstalk signal plus its reflection. What we are seeing at the far end is the backward crosstalk signal. Now, let's separate the forward crosstalk signal from the backward crosstalk signal. And we can do that by placing a transmission line in front of the coupled region. So we've got a coupled region that is 10 nanoseconds long. We'll put a 5 nanosecond long transmission line in front of it on both cases down here, both for the aggressor line and for the victim line. Now, when we send the signal down the trace, there'll be 5 nanoseconds before it hits the coupled region. Then it will generate a backwards crosstalk pulse, which will come back 5 nanoseconds to this point. It'll reflect off this point 5 nanoseconds later. It will come back to this point, and 10 nanoseconds later, it will show up at the far end of the victim trace. That's 25 nanoseconds. So we got 5 nanoseconds to here, 10 nanoseconds, 15 nanoseconds, 25 nanoseconds to get to the far end of the victim trace. The forward crosstalk signal will get to the far end of the victim trace after 5 nanoseconds and then 10 nanoseconds through here, or in 15 nanoseconds. So the backward crosstalk signal is going to lag the forward crosstalk signal by about 10 nanoseconds. And here's the results. Here is the driver. 10 nanoseconds later, the backward crosstalk signal shows up at the near end of the victim trace. In 15 nanoseconds, the forward crosstalk signal shows up at the far end of the victim trace. And at 25 nanoseconds, the backward crosstalk signal shows up at the far end of the victim trace. Now, if you look at these waveforms, suppose you had an oscilloscope and you were checking out your circuit and you saw these waveforms, would you know what they were? That's one of the reasons why crosstalk is such a difficult thing to troubleshoot. Now, let's add a termination at the beginning of the victim trace. Here was our basic simulation. We've got the aggressor line here, we've got the victim line here, but now we've got a terminating resistor here at the near end. Otherwise, it's the same as the first animation we showed. And here is the forward crosstalk signal showing up at the far end, 10 nanoseconds later. Here is the backward crosstalk signal at the near end of the victim trace. It's half the magnitude that it was before because it's not being reflected. And in particular, the backward crosstalk signal is not showing up at the far end of the victim trace at all because it's being completely absorbed by the terminating resistor at the near end of the victim trace. How about that? There's no backward crosstalk at all at the far end here because we absorbed it at the near end. And here's a comparison between not having a termination at the near end of the victim trace and having a termination at the near end of the victim trace. The backward crosstalk signal does not show up. And remember the animation we had of the terminated transmission line at the near end of the victim trace. The crosstalk signal comes back here but gets absorbed in this terminating resistor, does not reflect forward. In this situation, the backward crosstalk signal comes back here and reflects and does go forward. So at the far end of the victim trace, we do see a backward crosstalk signal that shows up here in the reflected case, but not in the terminated case. Now, all of those simulations were done in a microstrip environment. Let's do this now in a strip line environment. And this is going to be approximately 12 nanoseconds long. And here's the backward crosstalk signal that shows up at the near end. Here's the reflected backwards crosstalk signal that shows up at the far end of the victim trace. But now, there's no forward crosstalk that shows up at the far end of the victim trace. That's because in a strip line environment, the capacitive and inductive forward crosstalk components tend to exactly cancel. I say tend to exactly cancel, and they do exactly cancel as long as the environment is perfectly homogeneous and perfectly uniform. There are some times when that is not true, and so if it is not true that the environment is perfectly uniform, well, there might be a forward crosstalk that shows up. But if you're careful in specifying your board and in laying out your board, then you can completely eliminate the forward crosstalk signal at the far end of the victim trace by putting the traces in a strip line environment. And finally, we're going to put a termination at the near end of the victim trace in a strip line environment. And we look at the simulation, and here is our driver. Here is the backward crosstalk signal at the near end of the victim trace, but there is no crosstalk whatsoever at the far end of the victim trace. We have a strip line environment. We have a trace that is terminated at the near end, and no matter how close these traces are, and no matter how long the coupled region, there will not be any crosstalk at the far end of the victim trace under those conditions. And we thought crosstalk was a difficult topic. Haha. Okay, Now, the crosstalk coupling coefficient. Howard Johnson talks about this in his book, High Speed Digital Design, A Handbook of Black Magic, on page 192, and he gives this formula. The crosstalk coupling coefficient is proportional to 1 over 1 plus the quantity d over h squared, which we can expand to look like this. Now, it's important to recognize what his definitions of h and d are. H is the height of the trace above the plane. D is the distance between the center lines of the traces. In a lot of formulas, we talk about the separation of the traces as being the edge-to-edge separation. But this particular formula from Howie talks about the separation as being the distance between the center lines of the two traces. And that is because currents tend to run down the center line of the trace. Now, remember back when we showed the electromagnetic fields and the impact of separation? Well, if the traces are close together, there's a lot of coupling. If the traces are far apart, there's a lot less coupling. Now, we knew that, and we knew that intuitively, but this shows why that is the case. UltraCAD has a freeware calculator that will estimate the crosstalk coupling coefficient. In my experience in using this calculator, it's pretty good for a microstrip environment. There are so many variables in a stripline environment that it tends to overstate the crosstalk coupling in a stripline environment. But H is the height above the plane. You specify the rise time, you specify the parallel length, you specify the relative dielectric coefficient, and you specify the center line spacing, and whether or not there are terminations at both ends of the trace, and then calculate the crosstalk coefficient, which is expressed as a fraction and also in decibels. And we have 3 different types of configurations that can be used for estimating the crosstalk coefficient. So, takeaways from lesson 3.1. To minimize radiated coupling, EMI or crosstalk, minimize the loop area. That is just a great rule of thumb, no matter what. Minimize the loop area. Minimize crosstalk coupling by separating the traces. Forward crosstalk is minimized in a stripline environment, and backwards crosstalk may be controlled with terminations. In lesson 3.2, we're going to talk about printed circuit board design guidelines for EMI and crosstalk.